Okay. So, we have already discussed about random variable, right. So, that is something we have already done in the previous class. So, we have told that we will be probably starting discussing about random process, and that will be in next few class probably we will be occupying ourselves with the discussion of random process. How it is different from random variable, why it is important, so all those things, and then how to manipulate a random process. So that in our case where either the signal is random or the noise is random, we can actually analyze things. Okay. So, we will in the process we will also see if a random process passes through a system, because most of the time we will be passing signals through a system. So, how it interact with the system also, that will be something we will be discussing in next few classes. Okay. So, let us try to understand the basic fundamental difference between random variable and random process. So, I will start with an example which is probably a widely accepted example to understand random process. So, what we do is something like this: we take a resistor, okay, and we put a ammeter against it. Okay. So, no voltage source, nothing, just a ammeter against a resistor. So, what will happen? It will try to measure the current through the resistor. Okay. So, initially we will be wondering why there should not be any, I have not put any voltage, so there should not be any current. But what happens inside resistor? This is just a piece of wire probably, and inside that there are free electrons, and all those free electrons, or we should say charged particle, which are free to move. So, what will happen? They will be, because they are mobile, so they will be also doing Brownian motion. Okay. So, they will go here and there, they will get collided again, deflected back in a random fashion. Due to that Brownian motion, there will be some net current which will be recorded, okay. And that net current is completely random, because you never know how that net flow of overall electron density will be accounted, because it is all random motion. So, what will happen if you just see against that the current against that resistance? So, what you will see is something like this, a very low amplitude of current which is randomly varying, and this variation is over time. So, you are recording over time, and you are just through the ammeter, whatever you are getting, you are recording those values of current through that resistor in time. So, this is the nature you will be probably seeing, and it will just keep continuing. Of course, the amplitude will be very low, because it is just due to the Brownian motion. Okay. So, this random amount of current, if you now start giving a voltage source across this, so what will happen? Due to that voltage source, there will be a current, constant current, okay, across the resistance. So, immediately you will see that there is a DC shift to this particular random current, and on top of that DC, this DC shift will be due to this voltage source, and whatever the values of resistance, due to that whatever current you can calculate. Ohm's law you put, ammeter also, if you have something on that, you take that resistance also and you calculate overall current. You will see that current will be there, but on top of that there will be a random variation almost similar like that. Okay. So, that is due to that Brownian motion. Okay. However small that amplitude is of that current, there will be some amount of current which will be randomly varying. So, what we do now, suppose we prepare this same kind of resistance. So, we try to, this is a hypothetical experiment probably, we try to prepare same resistance, multiple number, and at the same time instance we say in the experimental this one laboratory. So, we say multiple students to actually measure with a similar ammeter across that resistance, and at every time instance they should record this currents, right. So, what we will see? We will see every student recording different kind of current pattern. So, if suppose this is for student 1, this is for student 2 and so on, and you will see that similar kind of current pattern, but which will have different random variation which will be recorded by different students. Okay. So, this is what will be happening, because it is, though they are identically prepared, at the same time they are measuring, because these are two different resistance, they are Brownian motion, they are independent. So, they will be means differently creating net current through the resistor, and you will be seeing something. And it is guaranteed that, because net means Brownian motion over a time, if you see, that should be 0. So, overall average current, if you wish to see, that will be all 0. Here also it will be 0, here also it will be 0, and so on. As many you can take, everywhere the average current will be 0, but there will be a random variation, and that random variation reported by student 1 will be completely different from student 2, and so on. Okay. That is what will be happening. Now, let us say we take this different signals. Okay. For a sufficient amount of time, they have measured it, they recorded it, they have given it to you. And now I fix a time, right. Let us say time t equal to t1. Okay. So, at that time instance, every student will be reporting some amount of current. Okay. So, take that value. Now, these values which are reported, if I have enough number of students, let us say almost infinite number of students, if I have that, then these things at a particular time instance, that means I have almost taken a snapshot of all these signals that has been produced by the resistor, identically prepared resistors by an experimented or measured current through it by different students. If I just take a snapshot at a particular time, we get different voltage reported, and then whatever we get, those will be random values at a particular instance. So, this is actually a random variable. At a particular time instance, if I take from different students different reading, whatever they are just like random variable, and over there we can construct whatever we have constructed so far. That means, we take those random variables, we can actually try to produce what is the PDF, associated PDF of that. We can also try to see what is the mean, what is the standard deviation, variance, and all those things, higher moments, we can produce all those things. Okay. So, we will be getting that. Suppose I decide, okay, no, T1 I am not happy with, I will go for another time, let us say that is T2, and again I do that. Okay. So, I take all those samples, again it is a random variable at a different time instance, right. So, there also I can again do all those things. Okay. So, I can get mean, standard deviation, variance, PDF, everything that I wish. Okay. What might surprise you is something like this. You go from this time to this time, you try to see the overall PDF of the random variable that you have recorded, you will see that will be same. That is very surprising, because this has been experimentally demonstrated that happens. Okay. Why that happens and what kind of class of signal those are, we will classify them later on, but this is something which happens. That means, there is something underlying which tells us that a particular signal you take, okay, which is random in nature. So, that means I can take different kind of those signals which are identically prepared, and then I take samples at a particular time instance from all those sample function we should call. Okay. So, remember, sample value and sample function, there is a difference between these two. So, this particular function, that entire function in time domain, that is called the sample function, whereas this at a particular time instance whatever value I am recording, that is actually sample value, and those values we are saying that forms a random variable, okay, right, and then I can get a PDF. But what we are now seeing is something more interesting, that the sample, if you take sample function, if you take a samples from all those sample functions and then try to evaluate the statistical property, they remains almost the same. So, that tells us that maybe something more has to be said about these things. Okay. So, in that means with that observation only, people started defining something else which is called random process. Which is, I should say, nothing but a random variable, but it is a function of time also. So, whenever we say x t, at a particular time instance this x is just a random variable, okay. But this random variable keeps on taking values at different instance of time, okay. And so, whenever it takes, if I just go through the time and takes different values and I construct a function, that becomes one sample function of a random process from which it is drawn. So, the associated random process is just that experiment of putting identical resistor and then measuring current through it, which is completely generated due to a inside randomness happening, which is called Brownian motion. Okay. Due to that, whatever current is happening for the entire time duration, if I record the overall sample function, those sample functions are now random, because as you have seen, one particular sample function is quite different from the other sample function. Okay. So, we can even say that as if like random variable, suppose head and tail. So, you have two outcomes, and whenever you do experiment, one of them are chosen, right. Here also I can say that as if there are different kind of sample signals, and when you do a experiment, one of them are chosen, okay. Which one will be chosen? It completely depends, okay. So, I will give you one very simple example, probably that will take out the doubt from use. So, let us say we have a 4-bit signal which is being transmitted. Now, I know that it is 4-bit, each bit of duration t, okay. So, t might be anything, it might be 1 second, or it might be 1 millisecond, 1 microsecond, whatever it is, we are not bothered about that, but it is just a 4-bit representation. That means 4-bit pattern, which is completely binary, it can only take 1 or 0 value, right. But whether it will be a particular bit will be 0 or 1, that is something I do not know beforehand. Means when we are at the receiver beforehand, I do not know whether this is 1 or 0, it can be anything, okay. Now, suppose the first bit I receive, I see that that is probably 1. So, I can construct the first bit, that is 1. Then I receive the second bit, I see that that is also 1. Okay. Then I receive the third bit, it is 0, and the fourth bit is 1. Okay. So, immediately I can see after receiving the whole sequence, I have a pattern which is being received, but this is actually one of the random pattern that could have been generated at the other side. This is just one of them. This is the sample function that I have received, but I could have received equally likely other sample function also, like it might be 0, 0 followed by 1 and then followed by 1. It could have been this sample function, or there might be multiple such things. How many of them will be there? Because each bit has 2 options. So, it is 2 to the power 4. So, there will be 16 options, just like you are rolling a die or tossing a coin, right. It has 2 options, or this one rolling a die has 6 options, but there we do not have the notion of time, it is just single thing that you observe, right. You do not have that notion of time. Here we have the notion of time, it is random, what is coming I am still not knowing, it is just coming to me, and after I detect the whole sequence, probably I will know which sample function among those 16 possible things has received by me. But whatever it is, it has a randomness associated at every bit. So, that is what we are trying to characterize, that every time instance, probably here we just have 4 distinct time instance. Okay. So, there are many other time, but we do not have to specify them because it remains the same. If it is 1, it will be remaining same as 1 for the entire bit duration t, right. So, there are 4 time instance where it might change. Okay. So, it is a function of that time instance where things might change, and that randomness is already there. If I would have talked about just a random variable, then I could have sampled it over here and it is just 2 values, 1 or 0. Whereas, because I am talking about the whole signal, that is why we have 4 sample value, and each of them characterizes a particular sample function. Okay. So, you have to see them in conjugate and then only we will be getting an idea about what will be the overall sample function. In digital it is little bit easier because we have a countable numbers of options, right. So, 4 bit we already have 16 options, not more than that, not less than that, this many options are there. But if I just say it is a continuous signal like that signal generated by the register, okay. So, it can take infinite options. So, there might be associated with it, there might be infinite number of sample function which can take any value at any time instance, right. So, I can this way I can construct any other sample signal and all of them are basically a particular sample function, okay. Any of them might happen. So, this is something which is actually characterized by a random process. So, whenever we talk about random process, associated with it a signal comes into picture and that signal we talk about is a random signal, okay. That will be any of those possible signal that can be constructed. So, if you start talking about possibility, we know that at every time instance there is a upper level and lower level that can be created by this particular resistor, okay. So, of upper level and lower level of current, if I know that among this any voltage level at this time instance, again next time instance which is infinitely small distance away from that time instance you have considered, there also any random value it can take. So, you can now see there will be infinitely large number of possibilities of sample signal that you can produce, because immediately over here only it can take infinite amount of values and then the next one depending on what value it has taken it can take again another infinite number of values and so on. So, like that there will be some, means there are infinite number of sample signal and probably one of them will be coming to you, right. And it is not guaranteed that always that signal will be coming to you. So, you experiment it today probably one particular signal, next day probably it will be different, right. So, like that whatever it is we are saying that particular thing, that signals are represented by xt because it has a variation of time, whereas at every time instant it is a random variable. Okay. So, that is what random process is. Now, let us talk about characterization of a random process, right. So, whenever we say characterization of a random process, we have already talked about two things. One is you take a sample time, okay. So, or you take a snapshot and then try to see the statistical property of it. You will be immediately getting over all those sample functions some values at that time and you try to construct a random variable out of that and then try to see the PDF of it, okay, and all other moments, right. So, this is one way of characterizing it, that is all good, but probably this is not all that we can do, okay. There is something more. So, I have a signal like this, I have another signal like this. Now, what I wish to also see that at a particular time instance if I have this value, in another time instance whatever value I will be getting or whatever statistical property I will be getting, if I take the snapshot among all the signals, will that have any dependency on the statistical property that I have observed at an earlier or later time instance. So, this is also very important, that is there a statistical, we have talked about dependency, correlation and all those things. So, now we are trying to see that in time I am taking snapshot and immediately I am generating random variable. Another time I take a snapshot, immediately I generate another set of random variable, means another random variable with different set of values. These two things, are they dependent or are they not dependent, because that also comes out from the signal quality or signal specification and that characterizes the signal as well, because if there is a dependency I need to know what kind of dependency. Okay. So, it might happen that the signal, even though it is random, at a particular time it is, suppose it has picked one random number, but the next time instance because of the low pass nature, that means the signal does not vary too much. Okay. So, low pass nature means what? within some amount of time, it has only low frequency values, high frequency values are not there. So, within a certain amount of time it cannot really vary beyond something, that is called low pass nature, because the slope will be lesser than, means it has to be less than something, right. So, if that is the case, immediately see, I have already spoken that within this it can take from this value to this value, but then I can specify that whenever I from this to this I go, and if I know what is the maximum frequency it can take, immediately from here, if it has already taken a value this much over here, there will be a bound up to which the value can vary. This bound can only be calculated if I know the dependency. So, that is why it is very important that I also have some understanding about the dependency of a sample signal with respect to the previous or previous to previous, all those sample signal. So, what do I have to do then? We have already talked about random variable, and this is why we have talked so much about random variable, dependency, joint PDF and all those things. So, right now you can immediately see that two things which might be dependent. Okay. So, if I wish to characterize, what do I have to do? I need to go towards the joint PDF of these two random variables. So, a random process, I know that it is an infinite collection of random variables, and there should be associated dependency among them. So, if I need to characterize the entire random process, I need to actually capture all those dependency, or rather I should say the associated joint PDF of all of them. So, that is where the next part comes, where I will be characterizing a random process. So, what do I do? I wish to suppose x t is that random process. So, I wish to do a characterization, that means CDF I will be calculating. So, in CDF I will talk about x1, x2, xn. What are these? Sorry, I will put bracket, semicolon, again T1, T2, I will just explain what are these, Tn. What does this means actually? It is actually the sample we were having, we define a time T1, T2 and so on up to Tn. At every instance we say the associated random variable is here x1, here it is x2 and so on up to xn. Okay. So, these are the associated random variable, and what we are trying to do is at those time instance we wish to see the joint CDF of those random variables. I have told you that they might have dependency. So, I want to capture that full dependency. So, only way to capture that full dependency is get a joint PDF or joint CDF among them. So, this is what you will have to do, and remember it has to be done over all sample time. That means, this t will go towards infinity. So, every sample time you take, try to capture all those samples which will be the random variable, and then take the joint CDF of all of them, right. So, this will just specify that my probability that x at t1 is less than equal to x1, comma x at t2 is less than equal to x2, and x at t2 t3 is less than equal to x3 and so on, x at tn less than equal to xn. So, if I can characterize this entire probability, then only I know that entire random process I have captured it well, which is a daunting task. You can already see that if I have a signal, it is a continuous time, means, and then immediately you have infinite number of time instance, and at every time instance you need to actually get the joint PDF, that means, or joint CDF, that means that random variable at T1 must be less than equal to some specified value x1 and so on. That will give you the joint CDF x1, x2 and xn, right. And if you just do a nth order differentiation, you will get the CDF. So, Px this x1, x2 up to xn, that should be just nth order differentiation with respect to all these variables, right, dx1, dx2, and the CDF fx. So, once I have this, probably I know that I have characterized the whole signal, okay, which is already we could see that it is a daunting task. Okay. So, any random process characterization of that fully is really beyond our capability most of the time. So, therefore, what we will try to do is we will try to restrict ourselves, okay, try to see something and try to give some definition to it. So, what we will start doing is something like this, we will go to first order. Okay. So, what do we mean by first order? So, we will talk about mean. What do we mean by mean? That is defined as this. So, what we are doing over here is we just take one sample time, that is t, and then try to get the mean of it. Okay. So, a particular sample time and just calculate the mean. So, this is called the first order. Immediately what will happen? So, I have to mean means it is the value multiplied by the PDF. So, x, and in PDF, because it is a one sample, so I do not need that joint distribution, I only need one of them, right. So, at time t. So, I will be calculating this Px x at t dx. So, if I can do that, I will get my mean, right. So, this is the first order we will talk about. Okay. So, this is just we are trying to get the mean, or we are trying to characterize the PDF at a particular point. So, in time. So, in time just take a snapshot, try to evaluate the mean, or you try to evaluate the PDF. Once you get the PDF, you will be getting the mean as well. Okay. Next, we will try talk about the second order, that means at least 2 time instance we will take. Okay. So, that is called the autocorrelation function. You might have already seen a autocorrelation function, but that was a different kind. That was in time, we are just shifting it and multiplying the same signal. So, it was the same signal. Here it is not same signal, you have multiple signals, okay, but we will try to evaluate the autocorrelation function. What is that? We call that Rx T1 T2. So, it is 2 time. So, therefore, it must be at T1 I get the x, at T2 I get the same from that same random means sample signal, I take that and I take the average, overall average. This is, remember, there must be a joint PDF and it is average. So, it should be a double integral. Okay. So, it must be minus infinity to plus infinity, minus infinity to plus infinity. I take, suppose I pick value x1 at T1 and x2 at T2, and then I need to get this joint distribution, which is x1, x2 at T1 and T2. So, now I have to get at 2 time instance what is the joint distribution among them, okay, and dx1, dx2, right. This is all that I will have to do. So, basically I take 2 or infinite number of sample signal at T1, at T2, I just try to get the multiplication of these 2, okay, and get the joint PDF of them and then try to evaluate the overall average value. Okay. So, which is the autocorrelation function. Now, from this autocorrelation function you can see also, if I just make T1 equals to T2, it will just go back to the same time and then I will get the second order. So, that is why over here with the single this one I have not defined the second order or third order, because that will be just an outcome of this thing, where you just put T1 equals to T2, you will get back that. Okay. So, we have defined 2, so on, we can just keep on defining things. So, what we will do, we will just get an idea of how to define them at higher order, and then we will try to talk about the minimum requirement that we need to talk about, so that the signal is almost characterized. Okay. So, in the next class we will do that.